Let's talk about acid and base strength. So, strong acids are completely dissociated in water. Okay, so this means if these right here are the strong acids, if HCl is a strong acid, it looks like this. This is the Lewis structure. That means a Cl minus will pull electron density away from the H, and all of the H will dissociate into H plus, and Cl minus will be left. If it's considered a strong acid, this will happen 100% of the time. Completely, all of it will come apart. Okay, which means if this is the strong acid, that means the Cl minus cannot hold on to the H, which means this, which is the conjugate pair, this is strong acid, this is its conjugate base. This conjugate base cannot hold on to the H plus, which means it is a very weak conjugate base. Okay, so if it's a strong acid, the conjugate base Cl minus cannot hold on to the H plus, so it's a weak conjugate base. On this table it says that HCl is a strong acid. On the side, it is 100% ionized in water, okay, which means this base is very, very weak. Okay, on this table, HCl is the strongest acid and Cl minus is the weakest base. Okay, as you can see, H2SO4 is also a strong acid and HNO3. And as you can see, as related to the hydronium ion. So everybody around, above, all the acids above the hydronium ion are strong acids. You also must memorize 4 more: HClO3, HClO4, HBr, and HI. And you already watched the previous videos on why these are strong, and it's based on the structure. Please, if you have not watched that video, you must watch it now. Okay, so its conjugate bases will also be very weak. As you go down the list over here, CH4 has a negligible strength and acidity. It's not even an acid. Okay, so weak acids, let's say HSO4 minus, will only partially dissociate in water, so not all the H plus will come off, which means the conjugate base is very strong. Okay, so let's talk about CH4 right here. Substances with very weak acidity do not dissociate in water. Their conjugate bases are extremely strong. Okay, so let's talk about CH4. CH4 has a Lewis structure like this. You're asking this H to come off. Okay, as you can tell, carbon and hydrogen have very similar electronegativities. So this electron, these two electrons are going to be equally shared between the H and the C, which makes this bond very strong, a strong bond. Since that's a strong bond, the H will not come off. So this H will not come off, so it'll stay as CH4. Therefore, CH3 minus is non-existent. As you can see here, CH4 is a very weak acid. It's not even an acid, it's negligible acidity, which means the CH3 minus really wants to hold on to the H, which makes it a very strong base. Okay, so if you have these substances in water, they will compete. Here is H2O. Every substance above H2O are stronger acid than H2O. Every substance underneath it are weaker acid than H2O. So if you mix these with H2O, they will win as acids. Okay, let me show you an example. Here you have HCl that you're putting in water. Which is a stronger acid, HCl or water? Well, you can see HCl is above, which means it's a stronger acid, so this equilibrium will lie to the right. You will get more products than you will get reactants. So the equilibrium will lie to the right. So if you were to write K equilibrium, it will be a lot of products, which are the H3O plus and Cl minus. You're going to have a lot of this, and you're going to have very little of this, the reactants, which means this number will be big, which means K equilibrium will be big. So HCl is a stronger acid than water, so the equilibrium lies far to the right. K, in this case, because HCl is so strong, it's a lot stronger than H3O plus. It's way up here. This Ka is, this product is so big that this is really close to zero, close to nothing, okay? Which means this is huge, which means this number is really big. If you were trying to measure it, it's unmeasurable. So it's just, you're gonna say it's just really, really big. Okay, strong acids have really big Kcs. Okay, so now I'm changing K equilibrium to Kc. C means concentration. And now because they're acids, you can also write Ka. They're all the same thing. All ratio of products over reactants. Okay, now let's look at weak acids. This is CH3COOH. This is the acetic acid. And if you look in this list, it is right here. Okay, again, you can write it like this, or you can write it like this. CH3COOH. They wrote it as CO2H, so same thing. It's below the H3O plus. Well, actually, water's right here. It's still a stronger acid than water, so it's going to no, I'm sorry. So you have, okay, let me just look at this. So this is the conjugate pair, right? This is the acid. This is the base. Conjugate pairs. You also have another conjugate pair. This is the acid. This is the conjugate base. And these are conjugate pairs. So you have to look at this acid versus this acid because there are two of them, right? So you have, which is stronger, CH3COOH or H3O plus? You look at the chart and you can see that H3O plus is stronger, which means this will go to the left. Okay, so let me fix my thinking here. You're really comparing, these are the conjugate pairs and the conjugate pairs. You're comparing the acidity of HCl, which is the acid. This is the base. This is the acid. This is the base. Between the HCl and the H3O plus, since HCl here is stronger than H3O plus, it'll go to the right. Okay, making the Kc really big. Here you have CH3COOH versus H3O plus. CH3COOH is weaker, H3O plus is stronger, which means this equilibrium will lie to the left. So if you go Ka for the acid is equal to products over reactants, you're going to have more of the reactants because it goes to the left. So this number will be high, and this number will be low. So let's make up some numbers. So again, HCl is a stronger acid than H3O plus. HCl is a stronger acid. Than H3O plus, which means this will go to the right, which means Kc is, or K equilibrium is very big. Okay, let's look at here. You're comparing the acid and the acid here, the two acids. H3O plus is a stronger acid, so it goes to the left. which means their reactants are big. This is small. So if I were to plug in numbers, a small number and a big number, 1 divided by 1,000,000 is a very small number. So Ka will be very small, less than 1. Okay. Weak acids have low Kc or Ka. Kc is the same as Ka for acids. So let's go ahead and practice. For the following proton transfer reaction, use the table above to predict whether the equilibrium goes to the right or to the left. Okay, so we are looking at the conjugate pairs. This is the acid. This is the base. Here's the other conjugate pair. This is the acid. This is the base, because the acid has the H. So compare the two acids, HSO4 minus, HCO3 minus. You look at the chart. HSO4 minus. It's right there. And the other substance is HCO3 minus. It's over. HSO4 minus is there. HCO3 minus is there. So HSO4 minus is stronger. So this is stronger acid. So it's going to go to the right. So if it goes to the right, K equilibrium, Kc or Ka, same thing, will be more S greater than 1. And it goes to the right. Okay. Pause the video and try these. So I'm looking at the two acids. Here's the pair. The acid is the one with more H's, so this is the acid right here. Okay, and then here's the other pair. So this one has more H's, so this is the acid. So compare water with H2PO4. You look at the chart. Here's water and H2PO4. H2PO4 minus. H2PO4 minus. H2PO4 minus is stronger, which means this is stronger, which means it's going to go to the left. And Ka will be closer. It will be less than 1. Okay, and then over here, here's the acid. I can already tell because there's the conjugate base. It has less H's, and here's the other acid. So I'm comparing NH4 plus and water. So you look here. Here's water, and the NH4 plus is here. NH4 plus is a stronger acid. So which means it's going to the right. Ka will be greater than 1.